The night sky has always inspired curiosity and wonder. The first astronomers explored with their eyes and imaginations. People looked to the heavens, searching for guidance and understanding. Today, our view of the universe has changed dramatically. Advances in technology have led to telescopes that allow us to see a once hidden universe. Like X-rays and MRIs, which give doctors different views of our bodies, astonishing images from radio waves to gamma rays have given us new insights into many cosmic puzzles. We are now on the brink of another exciting era in astronomy, one in which new cosmic messengers, tiny particles called neutrinos, can be used instead of light. High-energy neutrinos are created in the most extreme environments in outer space, like massive exploding stars and near black holes. Finding these neutrinos will give us a new way to explore the mightiest cosmic engines in the universe. But what exactly is a neutrino? And how do we chase and capture something that is so small and elusive that its nickname is the ghost particle? To answer these tough questions, we will take an extraordinary journey to the South Pole, where we'll meet IceCube, a strange new type of telescope buried deep in the ice. IceCube was specially built to search for these high-energy neutrinos.
Neutrinos are amazing cosmic messengers because they are nearly massless, they are absolutely tiny, and they almost never interact.
Neutrinos are incredibly small, but through them, we study the whole huge universe.
So, when we go out at night and look at the stars, we are doing astronomy. We're seeing light beams from the stars. What we do with IceCube is exactly the same thing, except we see neutrinos.
This is our home galaxy, the Milky Way, a grand, gigantic city of stars. Our planet Earth and the IceCube telescope at the South Pole are located in the inner rim of the Orion Arm, about 26,000 light-years away from the center of the galaxy. The Sun is just one of 200 billion stars in the galaxy. Of the Sun's 8 planets, only one is rich with life. Our planet is home to a wide variety of telescopes. Many are on tall mountains. Some are in space. But only one is buried in a cubic kilometer of ice. To capture ghostly neutrinos, physicists need to cast a wide net, they need a huge detector. And they need a place where it's absolutely dark and transparent. The South Pole, with miles of clear, untouched ice, is the perfect spot for the IceCube Neutrino Observatory. Antarctica is a harsh, frigid continent. It wasn't until 1912 that the first humans reached the South Pole. The first was Norwegian Roald Amundsen, arriving only a month earlier than England's Robert Scott. Today, the South Pole is still a destination for discovery.
Graphic South Pole, USGS. I don't know. Guess South is there.
IceCube's explorations, however, begin deep below the ice. IceCube is the largest and coolest telescope in the world. There are no mirrors or lenses like a traditional telescope. Instead, deep holes were drilled 2.5 kilometers down, and over 5,000 light sensors, called DOMs, were lowered and locked into place. Building IceCube was an amazing technological challenge. IceCube is huge, bigger than the Statue of Liberty. Even the Eiffel Tower. IceCube is a gigantic cube of ice, a kilometer on every side. While neutrinos are plentiful, IceCube searches for the rare, high-energy neutrinos, and it looks in all directions, all the time. When a single neutrino collides with the nucleus of an atom in the ice, a muon is created. The muon then moves through the ice, producing blue light along the way. This is called Cherenkov radiation. Remember, deep below the surface, it's actually completely dark, but the ice is incredibly clear. The blue light will be captured by these sophisticated sensors and turned into a digital signal. Scientists will then examine these signals for patterns created by the high-energy neutrinos. The patterns will help them unlock secrets about cosmic rays, or the power behind black holes, or gamma ray bursts, the biggest explosions in space. The story of how IceCube began starts with Francis Halzen, professor of physics at the University of Wisconsin-Madison. He first envisioned an observatory below the ice over 20 years ago. This was followed by more than a decade of design and testing. Finally, after 7 years of construction and the efforts of hundreds of people around the world, IceCube was finished. Exploring the universe using high-energy neutrinos would no longer be just a dream. Quite a bit has been learned about neutrinos, but mysteries still remain. Let's head back to the surface and take a closer look. Neutrinos have 4 important properties. First, they're plentiful. They outnumber all the grains of sand on planet Earth, all the stars, even all the atoms in the cosmos. Second, neutrinos are incredibly tiny. Invisible to our eyes and even our microscopes, they are billions of times smaller than a grain of sand. Third, they move fast, practically at the speed of light. And fourth, neutrinos are neutral and they hardly ever interact. Trillions fly through your body every second, easier than light goes through glass. Neutrinos are the lightest particles in the universe. Everything else has more mass: the electron, the atom, a cell. Yet this ghost particle, that is so close to nothing, helps explain the most massive, most energetic objects in the universe. When bigger, unstable nuclei rupture, like when uranium changes into lead, they emit energy and neutrinos. Even bananas produce neutrinos from the natural radioactive decay of potassium. Neutrinos also appear when atoms fuse together, like in the sun. Every second, nearly 1 billion tons of hydrogen smash and stick together, making helium and energy and neutrinos. While photons produced inside the dense sun take up to 1 million years to reach the surface, neutrinos fly out in 2 seconds and reach the Earth in just 8 minutes, providing important information about the forces that power the sun. Neutrinos are also produced by cosmic rays. These high-energy charged particles slam into our atmosphere, producing a shower of new particles, including neutrinos. Solar neutrinos are very abundant and commonplace. Trillions sail through the Earth constantly. But IceCube is designed to catch far more rare, more extreme neutrinos, ghost particles that are created by cosmic rays and in the most violent phenomena in the universe.
A good fraction of the light in the universe is actually not made by stars, but by catastrophic events like explosions, collisions, supernova, black holes.
The IceCube team is extremely dedicated. Many journey to the South Pole and work through the tough, cold conditions. Their central point is here, the ICL, or IceCube Laboratory. The cosmic signatures captured below the ice are collected at the ICL.
Command and control for the entire detector, which is under us. And it goes out about 1 kilometer square from where I'm standing. And this is where we control the entire detector. It goes down 2 kilometers deep into the ice.
But how do you get 5,000 detectors way down there, below the ice?
It involves a lot of hose, and a lot of heaters, and a lot of hot water.
Any final thoughts?
Don't let your kids grow up to be Antarctic drillers.
While drilling for IceCube is a lot of hard and precise work, the idea is basic. Hot water at high pressure will melt cold ice.
She didn't even go out.
The drilling operations for IceCube were extensive. Over 17 million gallons of ice were melted to build IceCube, enough to fill 500,000 bathtubs. Each year, there are only a few months warm enough to do all the drilling, cabling, and construction. That is why it took 7 years to complete IceCube. Drillers are not at the South Pole anymore, but plenty of people are still needed to keep IceCube running. Let's look and see what it is like to live and work at the South Pole. You don't get up with the sun, because the sun is above the horizon for 6 months straight. This is what it looks like for one day. The day-to-day routines are similar to home. Despite sub-zero temperatures, people still work outside. It might be a little cold, but you can run around the world, literally. The IceCube team always has plenty of work to do, including shoveling snow. There are other science teams at the South Pole besides IceCube. It's a small community of a couple hundred people, all living and learning together. But each year, the work season comes to an end as the sun sinks lower and it gets too cold to fly planes and run machinery. Most of the IceCube group leaves the pole. They'll be working back home, trying to capture the elusive ghost particle. A few hardy souls remain to winter over. They keep IceCube running, and they get to experience the majestic, electrifying Aurora Australis, the Southern Lights.
Most of the neutrinos stream right through IceCube. Occasionally one will actually hit a nucleus in the ice head-on and make a nuclear explosion. This causes a flash of light.
When a neutrino does interact with the ice, nearby IceCube sensors light up at nearly the same time. This is called an event. When the neutrino smashes into an atom, a muon is created. The muon moves through the ice and interacts with ice molecules, producing Cherenkov radiation, the blue light. The sensors detect and record this light. To understand these events, physicists create animations like these. The colors indicate the time sequence of the recorded blue light. The sizes of the bubbles reveal the amount of light. These particles travel almost at the speed of light, so in real time, each event lasts only a few millionths of a second. The sensors don't keep their data secret. They send the information up to the surface. and then up to the IceCube laboratory. The information is beamed to a tracking and data relay satellite in space, where it is sent back down to Earth, to IceCube collaborators across the globe. They pour through the data. The neutrino events are literally 1 in a million, so it takes creativity and resolve to find answers. The scientists, like us, are driven by insatiable curiosity. Let's journey to the University of Wisconsin, the lead institution for the IceCube project in the capital city, Madison. Madison hosts the main data warehouse. Its team of physicists and technicians take care of IceCube 24/7, every day of the year. All the South Pole data is scrutinized carefully to learn what tiny neutrinos can tell us about the enormous universe. Back in 1604, in the time of Galileo, something very rare appeared in the night sky. A star exploded, a supernova. It was the last one seen in our galaxy. The star's brilliant, dying light lasted for months before finally fading from view. Today, we can still see the ashes from this explosion. The blast of a supernova is the death of a massive star. The star runs out of its nuclear fuel. It implodes, collapsing under its own weight. And then explodes. IceCube, however, is searching for phenomena even more extreme than a supernova. Far more powerful than an exploding star is a gamma-ray burst. One way in which a gamma-ray burst is created is the smashing of two neutron stars. Two dense stellar bodies, remnants of a supernova explosion, spiral closer and closer and closer. This punishing collision produces cosmic rays and the extreme neutrinos IceCube is searching for. Another generator of gamma-ray bursts, even more energetic, is a hypernova, sort of a supernova. A massive blue star, 100 times more massive than the sun, runs out of fuel and starts to collapse. This gravitational collapse is so dominant, space is warped to the breaking point. This is a black hole, a place of such commanding gravity that nothing, not even light, can escape. A hypernova demolition quite possibly sends high-energy neutrinos toward Earth, where IceCube waits patiently to capture the evidence. But there may be an even more powerful engine in the universe than a hypernova. Lurking at the heart of almost every galaxy is a supermassive black hole. Its extreme gravity pulls matter in, rips it apart, and produces particles with energies far beyond those produced by the biggest accelerator experiments on Earth. A supermassive black hole is also called an AGN, for active galactic nuclei. This punishing, gigantic whirlpool is generated by an enormous amount of mass, squeezed into a relatively small area. IceCube has captured the highest energy neutrinos ever measured. But new discoveries always come with new questions. Where exactly did the neutrinos come from? How are the tremendous jets in the AGN formed? IceCube scientists hope to unravel these intriguing mysteries and many more. It's astonishing to realize how far we humans have traveled over time. From recording the first constellations to our journey today, which transported us from the IceCube detector at the South Pole to the farthest expanses of the universe. Nature is very surprising. Each new telescope uncovers new mysteries to explain. Exploration will never end, so long as people remain curious and develop creative tools to see.
We have many reasons to build IceCube. Astronomy, looking for dark matter, studying neutrinos. But because nobody has built such a thing before, what we really hope for is a surprise discovery.
The people who work on IceCube are driven by their passion, their quest for discovery. Finding new ways to understand our universe by chasing the ghost particle.